Hello everyone, my name is Vishakha Sharma. I'm a senior principal data scientist at Roche Diagnostics Information Solutions, where I lead advanced analytics initiatives such as natural language processing and machine learning to discover key insights, improving Navify digital product portfolio. I hold a PhD in computer science, and today I will be presenting on the topic applying healthcare specific large language models to build oncology patient timelines and recommend clinical guidelines. I have a disclaimer. Roche has been one of the Johnson Labs customers since August 2018. This presentation has been prepared by Roche and Johnson Labs to provide a high-level overview of Roche use of Johnson Labs products. Nothing contained or stated herein or during the presentation constitutes Roche endorsement of Johnson Labs products. Johnson Labs is fully responsible for accuracy and completeness of any statements related to Johnson Labs products, including the product's performance. To start, let me share a couple of words on who Roche is, what drives us, and how we are harnessing the power of digital with our Navify solutions. Roche is a 126 years old company with headquarters in Basel, Switzerland. It has two main business divisions, diagnostics and pharmaceuticals. We know that the future of healthcare is linked with digital transformation. As one of the world's largest biotech and in vitro diagnostic companies, Roche has developed some of the most impactful health innovations that have benefited millions of patients all around the world. We are number one in vitro diagnostics and pathology. We have 27 billion diagnostic tests performed improving patient care. We are leading provider of cancer treatments worldwide. We have over 16 million patients treated with Roche medicines. Last year, we unified all digital solutions from Roche Diagnostics under one digital brand, which is Navify. With Navify, we will continue to innovate health delivery and impact patient lives. Navify digital solutions securely integrate data across care settings, deliver operational and medical insights, and accelerate access to innovation. You can learn more about it at navify.com. We have Navify Oncology Clinical Hub and Decision Support Solution designed to simplify and improve day-to-day clinical decision making and care coordination across the oncology care continuum. It does so by aggregating and organizing fragmented data, providing an intuitive longitudinal view of the patient's entire care journey that can be accessed and used by all members of the oncology care team. National Comprehensive Cancer Network clinical practice guidelines in oncology are a set of evidence based, consensus driven recommendations developed by the NCCN to assist healthcare professionals in the management of cancer patients. These guidelines cover various aspects of cancer care, including diagnosis, treatment, and supportive care. We can quickly reference patient specific recommendations from the latest NCCN guidelines to support evidence based care decisions. We can confirm the optimal treatment plan for a patient based on the latest NCCN guidelines or institutional pathways. Our smart navigation capability saves time by automatically opening up the most relevant section of the guidelines based on patient data available. Let's discuss our journey to build scalable NLP system. As we all know, most healthcare data is unstructured and is not available for quick consumption at point of care. We built an AI-assisted data abstraction solution. It leverages natural language processing and machine learning to auto-detect medical concepts and translate free text into data that is structured and enriched while reducing the burden of manual data entry. Unstructured healthcare data exists in diverse report formats, has multiple languages based on worldwide geographies. Semantic ambiguity in healthcare data concepts could be unclear or open to multiple interpretations. This can create challenges when analyzing, exchanging, or using healthcare data for various purposes, including clinical care, research, and healthcare management. Example synonyms, abbreviations, etc. Manual annotations can be labor intensive and subjective. We all agree that extracting relevant information from unstructured sources requires OCR and NLP techniques. Cancer care, healthcare data, and decision making are extremely complex. For instance, let's look at this mock timeline. In 2014, the patient was diagnosed with breast cancer, specifically in the right breast upper outer quadrant. The diagnosis was PT3N1M0, stage 2A. infiltrating ductal carcinoma grade 3 with ER positive, PR negative, and HER2 positive markers. In 2015, the patient underwent surgery, specifically a lumpectomy. In 2019, the patient experienced the first relapse with liver metastasis. Multiple liver masses were detected, classified as RPTXN M1 stage 4 adenocarcinoma, ER positive, PR negative, HER2 positive, consistent with the primary breast cancer. In 2020, the patient had second relapse marked by new bone metastasis and regrowth of liver masses. NCCN believes that the best management for any patient with cancer is in clinical trial. Participation in clinical trials is especially encouraged. Personalized healthcare depends on comprehensive, up to date knowledge that allows prompt diagnosis, treatment decisions, and coordinated care. So, extracting chemotherapy timelines from clinical notes involves a series of challenges. Individual mentions of relevant drug administrations, chemotherapy events must be extracted and mapped to appropriate medication terminologies. Each event must then be assigned a time extent based on the date of the note and any temporal modifiers and indicators, example, time expressions, identified alongside the medication event. The 2024 shared task on chemotherapy treatment timeline extraction aimed to advance the state of the art clinical event timeline extraction from EHRs. Specifically, this work focused on chemotherapy event timelines from EHRs of patients with breast, ovarian, and skin cancers. A subset of patients was annotated for bold entities, time expressions, temporal relations, and patient level timelines. The rest was considered unlabeled data. In subtask 1, gold chemotherapy event mentions highlighted in green and time expressions highlighted in blue were provided along with the EHR notes. The goal was to build the patient level timelines using bold annotations as input. Thus, the subtasks seek to explore the topics of temporal relations extraction and timeline creation if event and time expression input is perfect. In subtask 2, which is a realistic real world setting, only EHR notes were provided. Thus, the subtask aimed at developing an end to end system for chemotherapy treatment timeline extraction from patients' EHR notes. The EHR for each patient included all types of available notes, regardless of the relevance of the patient cancer. Example, radiology, pathology, clinical, oncology, discharge summaries, and progress notes, etc. A subset of patients were sampled to create the gold annotations. Two domain experts created gold annotations of the chemotherapy events, time expressions, and temporal relations. These represent instance level annotations. The gold dataset was split into training, development, and test sets. This table represents the gold label dataset, detailing the number of patients, clinical notes, and words across the training, development, and test sets. Words refer to the tokens separated by the white spaces. In general, timelines can be represented in different formats. We can describe a patient's treatment timeline in natural language, such as 2 cycles carboplatin and Taxol 9, 30, 13, 10, 20, 13, the example that we saw in the earlier slide, which is easy to understand by humans. However, it cannot be understood directly by the machines. Over the years, the research community has developed a parsimonious set of relations to express temporality between two events or between an event and temporal time expression. An event is an occurrence that can be positioned on a timeline, in this case, chemotherapy events, and the set of temporal relations are defined as before contains um, can be defined as basically can be defined as as before contains with inverse contains dash one, which is the equivalent of contained by, overlap noted on, begins on, ends on. And then, with this representation, the construction of chemotherapy treatment timelines can be naturally decomposed into the following stages: chemotherapy event extraction, team expression extraction, temporal relation classification, time expression normalization, and patient level timeline refinement. The time expressions are also referred to as temporal expressions and timex3. Here is a table that shows the distribution of events, timex3s, and t-links in the gold label dataset. Timex3 refers to the time expressions, and t-link refers to the temporal relations. We develop structure prompts to guide the system in identifying and extracting relations between pairs of entities. These prompts serve as cues for the system to recognize and analyze relevant information in the text pertaining to the specified entities. This process involved prompt engineering techniques aimed at refining the instructions within the relation extraction pipeline, optimizing them to extract more precise and relevant information during subsequent stages. Figure illustrates two prompts. Prompt one, which is on the left hand side, is the relation labeled from the pairs, and prompt two, which is the right hand side for the relation labeled from the separate list of drugs and the test. Prompt one was used for the submission and for the evaluation. We tried prompt two, but encountered challenges in labeling the relationships from the distinct list, right? The zero shot prompt gave us a reasonably high precision by leveraging the prompt templates that guided the LLMs to generate responses, and it closely matched the desired output without requiring explicit training the data for each class or category. So this is our basically this figure shows the end-to-end large language model pipeline. We leverage current state of the art large language models for this sheer task. Like we tested large language models like Llama 2, Mistral 7B with different sizes and architectures to determine which model works best for the relationship extraction. I think it is very critical to understand that healthcare specific large language models are highly accurate if you are applying them to our healthcare domain compared to the non healthcare specific models, right? And they're also very much production ready. And one of the example is basically this JSL Medlama 3 8B version 1.0. And if you look at this code, which is very easy to adapt and basically apply this model to our healthcare specific domain unstructured data, right? So I think I will say, just to conclude in the end that, LLMs are expensive at scale because of the computational resources, pre-processing can be expensive. It requires specialized talent, and also there are certain infrastructure costs, right? Inputs may not align with LLMs in intended purpose. LLMs training with personal data risk privacy and legal issues in outputs, right? Right. And then there could be algorithmic biases, like if they are trained on the biased data, right? So LLMs may hallucinate, generating incorrect information, and that could mislead diagnostic recommendations, false treatment suggestions. LLMs can summarize vast amounts of medical literature, and most GenAI solutions, LLM right now is just a user interface where we have input and output queries, and it's like a user interactions basically, right? We do have chatbots, virtual assistants powered by LLMs that can improve patient engagement and education. To summarize, in any organization, many multidisciplinary professions like medical professionals, clinicians, peers, providers, lawyers, regulatory experts, computer scientists, and patients have to bring their diverse expertise to ensure that LLMs are developed and used effectively, ethically, and responsibly. It creates tremendous opportunities, but also tremendous responsibilities. Use of large language models will be a journey for us. And towards the end, I would like to thank all the audience who are attending this talk. And we are a team of software engineers, data scientists, product managers. And here is our contact information, and Roche is hiring. Thank you so much.